Assalamu alaikum. Fahad Hassan, registration number 16 TE10. Today the topic of our discussion is fast Fourier transform. Before discussing fast Fourier transform, we need to revise the formula of discrete Fourier transform, which is x of k equal to summation n equal to 0 to n minus 1 x of n e minus j k 2 pi n divided by capital N, where capital N is the number of samples. इस फॉर्मूले से हमें ये पता चलता है कि अगर हमें किसी भी सिग्नल का DFT निकालना हो तो उसके लिए जो हमें नंबर ऑफ एडिशन करनी पड़ती हैं that is equal to n into n minus 1, where n is the number of samples. For example, अगर 4 samples हैं तो हमें 4 into 3 which means कि हमें 12 number of additions करनी पड़ेंगी. Similarly, number of multiplications are equal to n square or n into n. Now, what is the disadvantage of DFT? The disadvantage of the discrete Fourier transform is its computational cost, which is very large. Computational cost is a drawback of DFT. Now coming towards our main topic, fast Fourier transform. Why do we use fast Fourier transform? We use fast Fourier transform to minimize this computational cost, and the second advantage of using FFT is that we can reduce the number of computations. Now recall formula 1, which is of DFT. Here the term e minus j k 2 pi n over capital N is used. If we consider this term e minus j k 2 pi n divided by capital N to be equal to capital W capital N raised to the power of small n k, now coming towards the concept of circle. For example, if we have 4 samples, which means capital N equal to 4, so we will divide our circle into 4 equal parts, and if we have capital N equal to 8, we will divide our circle into 8 equal parts, and so on. If we divide our circle into 4 equal parts, then we have W raised to the power 0 or equal to 1. Similarly, W14 equal to minus j, W24 equal to minus 1, and W34 equal to j. Another thing to note is that W0n is equal to 1 for all n, and W n raised to the power of n by 2 equal to 1 equal to minus 1 for all n. Now discussing even and odd decomposition. Now if we replace e minus j k 2 pi n divided by capital N with this term, then x of k becomes summation n equal to 0 n minus 1 n by 2 minus 1 x of n w n k n. Now this is the formula for even odd decomposition. When this n equal to 2r, so we say that it is even part, and when this small n equal to 2r plus 1, we can say that it is the odd term. Now coming towards an example, we have the following example. Let x of n equal to 1 minus 2 3 1 2 minus 1 2 1. Now in this we have n equal to 8, means we have 8 samples, 0 1 2 3 4 5 6 and 7, means that we have 8 samples. Now to calculate DFT, we need to do 8 into 8 minus 1, means 56 additions we have to do, and multiplications we have to do 64 multiplications. At 8 raised to the power 2 is 64 multiplications, which will be a quite tedious task. So in that case we used fast Fourier transform. Now how do we apply fast Fourier transform? Here is the answer. First of all, we have 8 samples, so we draw 8 lines for applying fast Fourier transform, and after that, after every in each of the 2 lines we have to draw this cross, and in the next stage we have to join the first line with the third one, second line with the fourth one, and similarly fourth line with the second one and third line with the first one. Basically this is a 4-point DFT for even terms and 4-point DFT for odd terms. We have arranged our even terms in this form: x of 0, x of 4, x of 2, x of 6. Similarly x of 1, x of 5, x of 3 and x of 7. Now after arranging in this form, we write the values of x of 0, x of 4, x of 2, x of 6, and similarly for the odd samples we do the same thing. Now what to do next is that now 1 plus 2 will be 3, so we write 3, and 1 minus 2 will be minus 1. Similar is the case for all other terms. After doing that, we need to consider the multipliers. We have two multipliers in the first four samples, W08 equal to 1, W28 equal to minus j, and similarly last two multipliers are in the next 4-point DFT for odd terms, which is 1 and minus j. So when there is no multiplier, we take the previous value and write it in the next stage, and if we have the multiplier, we multiply the value of multiplier with the previous value. For example, we have 5 over here and the value of multiplier over here is 1, so 5 into 1 is 5. Similar is the case for 4-point DFT we are applying at odd terms. So 3 plus 5 8. Similarly minus 1 minus j here, and when we will reach this line where there is written with the arrow head minus 1 and in the next line also minus 1, we will do, for example, 3 minus 5, so we get minus 2. Similarly minus 1 plus j, and in the final stage we have to join the first line with the fifth one, second line with the sixth one, third line with the seventh one, and fourth line with the eighth term, and eighth line with the fifth term, seventh line with the fourth, sixth line with the third, fifth line with the second. Now 8 minus 1 7, minus 1 minus j will add into minus 0.707 plus j, 0.707, we will get this term. And when we will reach where there are arrowheads, for example over here at the place of 9 we have an arrowhead minus 1, so we will do 8 minus 1 into minus 1 means 8 plus 1, so we will get the value of 9. Similar, we can get the similar values of x of k if we use the formula, which is to calculate x of 0 we use the formula e of 0 plus odd of 0 into W capital N K. So in this case e of 0 is 8, odd of 0 is minus 1, and W 8 0 is 1, so 8 minus 1 we get 7. So we can conclude that in FFT multiplications are reduced to n squared by 4. When we are applying FFT, then we have to do n squared divided by 4 number of multiplications, whereas in DFT we had to do n square multiplications, and the number of additions are also reduced by 1/4, because in FFT we have to do n into n minus 1 by 4 number of additions. So we can say that FFT is used by computers and modern devices to convert a signal in time domain, to convert a signal from time domain into frequency domain. That's all for this lecture. Thank you.